Today we're going to take a look at section 3.6, optimization problems. We've worked with optimization problems for the last couple of years, Algebra 2 and pre-calculus, and we've talked about these as being max-min problems. We want to maximize the volume or minimize the area or of something of that sort. And we also know these max-min problems as, or optimization problems as max-min problems. So some of the things that we're going to be looking at through the eyes of calculus now is being able to figure out where that maximum and that minimum occur. And we know through calculus that that max and min is going to occur when the first derivative is going to equal 0. So some things that we're going to be able to find, or we're going to want to be able to do with these problems, is first determine a primary equation. What do we want to maximize or minimize? Normally these are going to be two equations that we're going to have to combine into one, so we get down to one variable. If we can reduce down to a single variable, it allows us to find the derivative a lot easier than if we had two variables where we had to use implicit differentiation. Determining our critical points where our derivative equals 0, and we want to go ahead and check our max and our min problems, but we also want to make sure that we're okay with that domain. And we may talk about that here a little bit. Make sure that the answer makes sense. Can we have a negative value? Can we have a positive value? Those sorts of things that we have to check out. Alright, so first problem here, first example, we want to determine the maximum volume of an open box having a square base and a surface area of 108 square feet. So the first thing I like to do is go ahead and draw a figure of what we have. So there's my box. And what you want to realize is that this is an open box, so we don't have a lid to it. That's very important. Some of these are going to be a closed box, some will be an open box. You make sure you watch the wording of them. But we know that we have a square base. So our base here, if we go ahead and continue that out, we know is going to be the same. And then our height will be different. I'm looking to figure out the maximum volume. So I want to be able to find the volume of this figure. And we know the volume of a rectangular prism is going to be the length times the width times the height. In this case, we have x squared y. Notice I have my volume in a two-variable equation at this point in time. I want to be able to get this down to one variable. So I want another relationship between x and y. And we know the surface area of this figure is 108. So my surface area, recall, is taking the area of each of the surfaces. So I have an x squared, which is the base, and to that I'm going to add 4 of my sides. And my sides are each x by y. So I have 4xy. I also know the surface area is 108 square feet. So what I can do is go ahead and get this equation into terms of x, solving it for y. So y is going to equal 108 minus x squared divided by 4x. I can take this information now and plug it into my volume equation, and that's going to reduce this two-variable equation into a one-variable equation. So my volume is going to equal 108 minus x squared over 4x times x squared. Cleaning this up just a little bit, we can cancel out an x. So we have 108 minus x squared divided by 4 times x. And I could multiply my x through to get 108x minus x to the third over 4 as being my volume. Running out of room there, so let's go ahead and pull another sheet of paper in here. So what does that allow me to do? Well, I know then I can find the derivative of this to find my critical points. If we think about this as my 4 in the denominator, there's no variable to it, so I can write this as 1/4 times the derivative of the numerator, which is 108 minus 3x squared. Since I have the derivative, I can set this equal to 0 to find my critical values. I can multiply my 4 over, so I have 108 minus 3x squared is going to equal 0. Solving for x, I get x squared equals negative 108 divided by negative 3, which is 36. So I'm going to get my x value, if I take the square root of both sides, as being plus or minus 6. Now this is where the idea is, check on your domain. Does it make sense that x would equal a positive 6 or a negative 6 or a negative 6? And if we think about the x value. The x value is the side length of our box. So we know that we can't have a negative value. So the only value that is going to make sense on our domain is going to be x equals 6. So as I look at x equals 6, I can go ahead then and figure out, is this going to be a maximum or minimum value? Since I only have one, it's going to be my maximum value. So I can go ahead and plug in my 6 in to figure out my y value. I'm going to plug that into my surface area. Oh, we knew that 108 is going to equal my x squared, which is 36, plus 4 times x, which is 24y. Go ahead and solve that. We can subtract that. We get 72 equals 24y. Divide by 24, so 3 is going to equal y. So in this case, we know that x is going to equal 6, and our units on this is feet, and our y value is going to be 3 feet. And that's going to give us our maximum volume that we're going to have. In our next problem, we're going to have the point closest to a parabola, or on a parabola of 4 minus x squared, that's closest to the point 0, 2. So if we think about what we have here, again we can draw a picture. 4 minus x squared is going to look something of this form, where we come up here to 4. The point 0, 2 is here. So I'm looking to minimize the distance into this parabola. And we don't necessarily know where that parabola is going to go through, and we don't know where my distance is going to be the shortest. So that's what we're going to be looking for. So what do I want? I want the distance between 2 points. So my distance formula is the square root of the difference of the x's squared plus the difference of the y's squared. Well, I know that I have a point 0, 2, so my distance is going to be between, and we don't know what the point is on the parabola, so we call that x, y at this point. So I know that I have x minus my x value, which is 0 squared, and to that I'm going to add the y minus my y value, which is 2 squared. Clean that up just a little bit, we can have the square root of x squared plus y minus 2 squared. Again, I have my distance in 2 variables, so I want to go ahead and get that down to 1 variable. What do I know about x and y? I have the relationship that y equals 4 minus x squared from the parabola. So I can go ahead and take that 4 minus x squared and plug it in for my y. So my distance is going to equal the square root of x squared plus my y value, which is 4 minus x squared minus 2 squared. I'm going to go ahead and clean this up. So I get the square root of x squared plus 4 minus 2 gives me 2 minus x squared squared. And cleaning that up just a little bit more, we have x squared. 2 minus x squared squared is going to be 4 minus 4x squared plus x to the 4th. And cleaning it up just a little bit more, we have the square root of x to the 4th minus 3x squared plus 4. Now I'm ready to go ahead and find my derivative. So d prime. I have a chain rule, so I'm going to have 1/2. Inside stays the same, 3x squared plus 4 to the negative 1/2, and then multiplied by the derivative of the inside. So 4x to the 3rd minus 6x. Again, we're going to start thinking about our domain and what things can happen and where things are going to happen for us. So if we think about when we set this equal to 0, remember critical values are where the numerator is equal to 0, where we have horizontal tangent lines. We're also interested in where the derivative is undefined. But if we think about where the derivative is undefined, that's in our denominator, where our denominator equals 0. If our denominator equals 0, then that's going to be an asymptote. We should think about the asymptote. The asymptote is where it's undefined. So we're really not interested with our max-min problems where our denominator is equal to 0. That's going to give us kind of an erroneous solution there because it's not going to give us a value of use. So really we're only interested in that numerator being equal to 0. So I have 4x to the 3rd minus 6x equal to 0. I can go ahead and solve that for x. I can pull out a 2x if you wish. So we end up with 2x squared minus 3 equal to 0. So I get first critical value of x equals 0. The second critical value, coming from 2x squared minus 3, I get x equals, add 3 over, divide by 2. So I get x squared equals 3 halves. So x is going to equal plus or minus the square root of 3 halves. If we think about these two answers, actually any one of these answers, all of these are possible solutions for us, because we can have x equals a negative value or a positive value or 0. So what we're interested in then is finding which one of these is the maximum and which one's the minimum. How do we find that? Well, we first have then to go and look into our distance. Remember, our distance was equal to the square root of x to the fourth minus 3x squared plus 4. So I'm going to go ahead and take and plug in these values into my distance to figure out which one's the maximum, which one's the minimum, or maybe they're all maxes or all mins. We don't know. So closest means minimum, so we're looking for the minimum value. If I plug in 0, that's kind of an easy one. Square root of 4, it gives us 2. So I get the point, or the distance, I guess, of 2. If I plug in the square root of 3 halves, then my distance, so if I plug in 3 halves, and I take that to the fourth, so I have 3 halves to the fourth, minus 3 times the square root of 3 halves squared plus 4. As I'm doing this, in my mind I'm thinking, hey, wait a minute. If I think about the negative square root of 3 halves, and I plug that in as well, anything to the fourth power is going to be a positive, anything to the second power is going to be a positive. So it doesn't matter if I get a positive or a negative x value, they're always going to be the same answer. So I know that these two are going to give me the same solution. And I'm going to get the square root of that. So if I take the square root of 3 halves and take it to the fourth, that's going to give me 9/4. Minus, if I take the square root of 3 halves squared, I get 3 halves plus 4. So here I have 9/4 minus 9 halves plus 4. Square root of that. 9/4 minus 9 halves. What is that? Negative 9/4 plus 4? Nope, just positive 9/4. 9/4 minus, let me put it in the calculator. 9/4 minus 9 halves. Yeah, I was right, negative 9/4. And to that I'm going to add 4, just didn't look right to me. Alright, and that's going to equal the square root of 7/4. So, if I have the square root of 7/4, that gives me the square root of 7 over 2. If I take the value of that, the square root of 7, divided by 2, that gives me a 1.323, so on and so forth. So my maximum would be occurring at 2. My minimum is going to be here at the square roots of 3 over 2. So my minimum distance, the point that's going to give me that value, is going to be my x value, which is the square root of 3 halves, and negative square roots of 3 halves, and I got to find my y value. To find my y value, I can come back up here to 4 minus x squared. We'll come right over here, 4 minus x squared, so 4 minus the square root of 3 over 2 squared. That gives me 4 over 9, 3 halves. Alright, so we have 3, I know it's kind of ugly there, 3 minus 3 halves, then we got 8 halves, so we end up with 5 halves. Again, it doesn't matter if we plug in the negative or the positive of that, we still end up with 5 halves. So that's going to be my minimum point, my minimum, my point that is closest on that parabola to that point. So in this case, we had to use, and we had to go back and look at those values. Alright, we'll do one more. We had a few other ones, so it seems like we're getting a little on the lengthy side here. A farmer has 2,400 feet of fencing. This was one that we saw in Algebra 2 and Pre-Calculus quite often. So we had this river, we have this rectangular area that we wanted to fence in. So we know that this is x and y. We have 2,400 feet of fencing to use. So to go around the perimeter, we had 2x plus y equals 2,400. And then if we look, we want to maximize the area. Our area in this case, area is going to be xy. So if I want to go ahead and get this into one variable, I have y equals a negative 2x plus 2400. I can take that information and plug it in for my y into my area. So my area is going to equal x times negative 2x plus 2400. And our area then is negative 2x squared plus 2400x. I go ahead and multiply it out in order to be able to find the derivative pretty easily. So our a prime, our derivative is negative 4x plus 2400. I'm going to go ahead and set that equal to 0. So x is going to equal 600 feet. Again, we only have one critical value, so that's going to be our maximum area, where our maximum area is going to occur. So when x equals 600, can we find our y value? And we know that y equals negative 2 times that x value plus 2400. So if I plug in 600, I get negative 2 times 600. Let's see, negative 2 times 600 plus 2400. Go ahead and add that together. We get negative 1200 plus 2400, or 1200. So our y value is going to be 1200 feet. So in order to maximize our area, we're looking at a region that is 600 feet by 1200 feet. So that gives you an idea of where we're going to see these max-min problems and what we can do with them. If you have questions, please reach out, let me know, and we'll discuss them. Good luck, enjoy, and happy max-min problems.